this is here quite a challenging question actually, because we've got a weak but concentrated base this time. We've been given the concentration of this base, and we are required to find the pH of this solution. And we've got the pKa of the conjugate acid for this base. So before we get started, we need to write down what we would expect. So we are dealing with a base, and therefore we would expect that the result, the pH that we get, must be larger than 7, because that is the definition of a base. Okay, so what have we got? It's always a good idea to write down what is going on in this solution. So we have, let's say we've got a base. This here is my base, and it would react with water. It is a reversible reaction, but because it is a weak base, it's pretty much on the left-hand side, the equilibrium. And we would get the conjugate acid plus OH minus. Now, of course, we've got OH minus. We don't have any proton concentration, so we need to bear that in mind when we use our pH calculation. Now, we can actually formulate an equilibrium for that. So the equilibrium for the base would be the concentration of the hydroxide times the concentration of the acid, once the equilibrium has established itself, divided by the concentration of the base that's left. And we don't need to write the water because that is implicitly included. So that is our equilibrium constant written as these concentrations. And we also know that for each of these, of the acid that we produce one hydroxide ion. So we can write OH minus must be the same concentration as the acid that is generated. And for the base that is left in the equilibrium, we would have the concentration of the base that we had at the beginning minus what has been already dissociated then in the equilibrium, which would be minus OH minus concentration, the concentration of the hydroxides. Now, because this is such a weak base, this is really almost negligible, this OH minus, and instead we just simply can write that this base concentration, it doesn't really change a lot. So it is pretty much the same that we had at the beginning. Now with that we can write our equilibrium. We can write this as OH minus squared divided by the initial concentration of the base, and that would be this concentration here. And of course we can rearrange that a little bit, and we can write the OH minus concentration squared equals Kb times the initial concentration of the base. So what can we do with this? Well, we can take both sides negative log to the base of 10, and with a little bit of simplification we would get the equation POH equals 1/2 of pKb minus log to the base of 10 of the base concentration. And this is really the equivalent equation to what we can do when we are dealing with a weak acid. Now it is just simply for a base. So we've got POH and we've got pKb. But unfortunately we are not looking for POH, we are looking for the pH. And we can use the equation pH plus POH equals 14. So we can convert the POH into a pH, and we can also convert pKb, because we don't have a pKb, but we've got pKa. We can use a similar equation, pKa plus pKb is also 14 in water. And we can use these equations to calculate the pH. So we can write pH equals 14 minus POH, and instead of POH I just simply write what I've written here equals 14 minus 1/2 of, and instead of pKb, I can write 14 minus pKa. So instead of pKb, I write 14 minus pKa, and we still have the negative log base 10 of the base concentration in this bracket here. So now I can start to do the calculations here. So we've got 14 minus, and I can multiply this negative half into this bracket here. So that would be minus 7. Minus times minus is plus, plus pKa over 2 plus log 10 of A of the base again, also divided by 2. Or I can write this a little bit nicer. So the pH is 7 plus pKa plus the log of the base divided by 2. So that's a nice equation that I can use here for the pH in this case. And now I just simply put in the numbers. So pH equals 7 plus the pKa is 2.57. 2.57 plus log to the base of 10 of the concentration of the base. So that is 9.72 times 10 to the minus 3. I need to be careful because this needs to be, this concentration here, this needs to have the unit of mole decimeter to the minus 3 or mole per liter, which is also abbreviated by m. And we must not forget to divide this by 2. So that would be the numbers. And if we put this into a calculator, we would get 7.279 for our pH. Now, we need to check what we've just calculated. So we've got a pH that is larger than 7, and initially we said we are looking for a pH that is larger than 7, so there is we can be quite confident that this calculation actually worked out all right. So what we had to do in this example was we had to work with Kb, we had to work with an hydroxide concentration and find the pOH of the base first, and then convert the pOH into a pH by also using the knowledge that pKa and pKb added together also gives 14. So this is a little bit of a challenging question, and yet I think I hope it makes sense, and thank you very much for watching.